All right, let's talk about making AI fast. I mean, really fast. Why is it so hard to make AI feel, well, instant? We're going to dive into how a super smart caching system called LMCache is completely changing the game, making our AI models faster and way, way more efficient.
You know that feeling, right? You type out the perfect prompt, you hit enter, and then there's that frustrating pause before the AI even starts typing its response. And look, if you felt this, you're not alone. This is a massive headache that developers are throwing everything at to fix.
Okay, so what is that pause? Turns out it's not just in your head. In the world of AI infrastructure, that waiting period is actually a super important performance metric. And honestly, it's one of the biggest bottlenecks we're facing in AI right now.
And yeah, this delay has a name. It's called time to first token, or TTFT for short. Think of it like this. You ask someone a question and they just stare at you for a couple of seconds before they even start to answer. It's awkward, right? It feels slow. That's exactly what's happening with AI. A low TTFT makes an AI feel snappy and responsive, but a high one just makes it feel, well, broken. So what's the culprit here? Well, the main villain is something we call redundant computation. Imagine you're having a chat with an AI about a project, and for every single thing you say, the AI has to go back and re-read the entire conversation from the very beginning. Every single time. That's pretty much what these models are doing. They're just burning through power, relearning stuff they literally just saw a few seconds ago.
Okay, so how in the world do we fix this wastefulness? Well, the answer, or at least a big part of it, is in something called the KV cache. And this is really at the core of how these models think.
You can think of the KV cache as the model's short-term memory. It's that simple. As it's processing your prompt, it stores key calculations, these key value pairs, so that when it generates the next word, it doesn't have to start from square one. It's a really important optimization that's already built into these systems. But here's where things get, frankly, a little insane with the old way of doing things. Just look at this flow here. After all that hard work of processing the prompt and generating a response, that super valuable KV cache, it just gets tossed in the trash. Deleted. Gone. Which means the very next person who comes along and asks a similar question, yep, the model has to do all that work all over again, right from scratch. It's just a colossal waste of energy and time.
And this is the exact problem LMCache was designed to fix. It's basically a brilliant system that says, hey, let's stop this ridiculous cycle of throwing away perfectly good work.
So LMCache slots in as this really smart acceleration layer. To put it simply, instead of letting the AI model just junk all its recent computations, LMCache is like, nope, I'll take that, and it saves the KV cache. And what that means is, the next time a similar request comes in, a huge chunk of the work is already done. It's ready to go.
And as you can see here, its goals are pretty straightforward, but wow, are they powerful. First, slash that time to first token. Second, save that super expensive GPU memory by offloading these caches. Third, let multiple servers share the same cached work. And finally, and this is huge, it needs to plug right into the tools people are already using, like VLM, without a bunch of hassle.
Okay, so that's the big idea. But how does it actually work? Let's pop the hood and take a quick look at the architecture. This diagram here really lays it all out. So when a request from a user comes in, it doesn't just go straight to the big LLM engine. No, first it has to go through LMCache, which acts like a smart traffic cop. Let's break down what happens from there.
So, LMCache looks at the beginning of the prompt and basically asks one question. Hey, have I seen this before? If the answer is yes, that's what we call a cache hit right here on the slide. It just grabs the save data, and boom, we're off to the races. If it's a new prompt, that's a cache miss. No problem. The request just goes through the normal process, but, and this is the important part, LMCache then saves that new computation so it's ready for next time.
Now what's really clever here is where LMK stores all this info. It uses this multi-tiered system you see in the table. I love this analogy. Think of the hot tier on the super-fast GPU as the stuff on your actual desk. You need it instantly. The warm tier in the CPU's RAM, that's like your filing cabinet. It's quick to get to, but not right there. And the cold tier on a disk, that's the archive room down the hall. Perfect for long-term storage. And the best part is, it manages all this storage completely on its own. It uses a smart policy called Least Recently Used, or LRU, which is just a fancy way of saying it's always tidying up. It's just like cleaning your desk, right? If you haven't used a file in ages, you're going to put it away in the filing cabinet to make room for what you're working on today. LMCache does exactly that, making sure the fastest memory is always reserved for the most important data.
Okay, so this whole smart tiered storage system, it sounds great in theory, right? But what's the actual payoff? Let's get to the results, because honestly, the performance gains here are just staggering.
All right, first up, the big one. Time to first token is 6.7 times faster. Let that sink in. Nearly 7 times faster. That's the difference between an AI that feels like it's wading through mud and one that feels like it's reading your mind. It's instant.
Okay, next up, resource use. Since the GPUs aren't just spinning their wheels redoing the same work over and over, their total usage drops by about 32%. Now, for any company running these models at scale, that is a massive cost saving. It's like getting a huge discount on your power bill and your hardware costs, all at once.
And all of that new efficiency, it translates directly into more raw power. We're talking about an 80% higher throughput. What that means is the system can handle almost twice as many users at the same time. It's basically like turning a clogged 2-lane road into a wide-open 4-lane highway.
So let's just take a second to look at this summary table, because these numbers really tell the whole story. That time to first token, it dropped from over a second all the way down to just 0.18 seconds. Insane. The GPU, which was basically redlining at 92%, is now cruising along at 63%. And throughput, the number of requests it can handle, went from 1 per second to almost 2. It's nearly doubled. Look, these aren't just little tweaks around the edges. These are absolutely game-changing improvements.
So let's pull back for a second. What does all this technical stuff and all these numbers actually mean for the rest of us? Because this isn't just about making a chatbot feel a little bit quicker. This goes way deeper. This is about the future of AI itself. See, clever optimizations like LMCache are what make large-scale AI sustainable in the long run. When you drastically cut the cost, the hardware, and the energy you need for every single interaction, you open the door to building way more powerful AI tools that more people can actually afford to use. This is how we democratize AI. This is how we take it from being this expensive tool for a handful of big companies and turn it into a utility that's available to everyone.
And you know, this final quote from the paper really just hits the nail on the head. Reusing what's already been computed, I mean, it sounds so simple, right? It's such a basic idea, but the impact is just massive. What LMCache proves is that the next big leap forward might not come from building an even bigger model, but from just working smarter with what we already have. And it really makes you wonder, what other huge wasteful problems are just hiding in plain sight, waiting for another simple, brilliant solution like this?